Hi, in this video we're going to go over some section 1.2 examples. So first, let's go over the idea of rooster in set notation, and let's go with some exercises on it. So first, we want to write all the sets using set rooster notation. We have the set of all the odd positive numbers less than 10, and so we're looking for the numbers that are less than 10, so up to 9. Positive integers, so starting from 1, and that are odd. So that's going to have 1, 3, 5, 7, and finally 9. This 7 came out weird. Okay, something similar, the set of all even integers between minus 5 and 5. Notice that that is inclusive, so that is going to include the minus 5 and 5. So, oh wait, but they're even. So because they're even, then it doesn't really, but even minus 5 and 5 doesn't matter. So we have minus 4, we have minus 2, 0, 2, and 4. The set of all multiples of 3 from 0 to 15. So we have 0, because 0 is a multiple of 3, 3 times 0, 0, 3, 6, 9, 12, and finally 15. Now, question number 2 is describe all the following sets in words. So this would be the set of x, where x is even. And we can even call it maybe the natural numbers or positive integers. So we can simplify this a little bit. We can say this is x that belong to the natural numbers, so that x is even. This is one way of representing this. On this one, we have multiples of 3. Notice 0, 3, 6, 9, but we also have negatives. So we're going to say x belongs to the integers, but x multiple of 3. Okay. Then we have another one, minus 0, 1, minus 1, 0, 1. And this is something that we can see as the integers or the set of integers, so that x is between minus 1 and 1. And it's inclusive, so it matches there. You can write that in set builder notation like I'm doing here, or you can write that in words. The solutions that I'm going to pose, I'm going to put that in words as well. So this will be complementary to this. So question number 3 asks, are the following statements true or false? Explain your reasoning. So we have the set of 1 to 3 is equals to 3 to 1, 1, 2. And this is true. This is true because it doesn't matter if I have repetitions. So this, by the extension axiom, these are two sets that are equal since they have the same elements. Doesn't matter that we have repetitions. B is the set of the natural numbers equals to the set that contains the natural numbers, and this is false. The natural numbers has infinite element, while the set that only contains the naturals is going to have one element only. So those are different things. Here you're using the elements, the set as an element. Is the set of 0 equals empty? No. The set of 0 has one element, while the empty set has 0 elements. Okay, so you gotta be careful with this. Now, for set builder notation, notice that this is the interval between 0 and 5. And we can describe this as the integers between 0 and 5. inclusive at 0. For this one, we can say this is the integers that are bigger than 3 and less than 4. Or this would be equivalent to just saying a couple numbers here. We can actually list them up. We can say this is -2, -1, 0, 1, 2, and 3. And this will list all the elements in here. So that will be a pretty good description. Here, n equals 3k, where k is an integer. Notice that these are multiples of 3k. So we can kind of go ahead and do 0, 3, 6, 9, and go onwards. And here we can go -3, -6, and go onward on the opposite direction. So that's a good description for this sets. Now, question number 5. We have A, B, and C and D doing the set A, and B is the set done by the element B, D, and F. The set C is A and C. And we want to determine if these things are true or false. First is C is a subset of A, and that is actually true. Notice that every element in A is an element in, every element in C is an element in A. Since for X in C, we have that X belongs to A, then we have the C is a subset of A. Is B a subset of A? And the answer is false. Why? Because in particular, F belongs to B, but F does not belong to A. Is A subset of A? Yeah, this is true, because every element of A is in A, so that's going to be a subset of itself. Is C a proper subset of A? This is true, because there are elements on A that are not in C. For example, D belongs to A, but D does not belong to C. And we have that C is a subset of A. So it is a proper subset. For question number 6, here we're doing Cartesian plane. So we want to first find x times y on pairs. So I'm going to do all the pairs with 1. So 1a, 1b, 1c, and then I can do all the pairs with 2. 2a, 2b, and 2c. Now yx is going to be actually the opposite. I'm going to start with a1, a2, then b1, b2. The order matters a lot when you're doing Cartesian products. So that's why x times y is so different from y times x. And if we're doing x times x, then this is essentially the pairs with itself. So 1, 1, 1, 2, and then 2, 1, 2, 2. It's using x both as the x and the y. So we have is 2a belongs to x times y, and the answer is true. Is a2 in x times y, and then the answer, as you can see, is false, because this doesn't start with letters here in x times y. Now moving on, let's go to this multiple choice question. Is 3, 5, the pair 3, 5 equals to the pair 5, 3? This is false. Remember that for order pairs, the order matters. So this is 3 belongs to, if we have 3, 5, then that means that 3 belongs to the first set and 5 belongs to the second set. So the pair 3, 5 is never going to be 5, 3. In particular, 5 might not even belong to the first set. Now, for sets, that's a different thing. So the set of 3, 5, it is the set of 5, 3. This is true, the order doesn't matter. What is the difference between this and this? Well, this is an order pair, and this is just this is a set. It's different in terms of notation. Now, once again, now we're going to consider the Cartesian plane. So how many elements do we have in A? How many elements do we have in B? How many elements we have in A times B? So first and anything, well, we have 3 elements here, and we have 2 elements here. So the number of elements in A times B is the number of elements in A times the number of elements in B, which is 3 times 2, which is 6. Now let's have all the elements of A times B. And once again, this is just doing 1x, 1y, 2x, 2y, and 3x, 3y. So there you can see the 6 elements. How many elements are in B times A? B times A is going to have exactly the same amount of elements because we're just multiplying backwards. And so it's going to be x1, x2, x3, and then we're going to have y1, y2, and then y3. Those are all the elements. Is A times B equals B times A? No. And you can see that they're not, because the elements are not the same. These are not the same as this. So they cannot be the same. Now, question number 9. So for question number 9, we have write the following sets using self-builder notation. The set of all the positive even integers. So we're going to take elements that belongs to C, so that x is sum to n for n that is also on the integers. So this is giving me all the evens. All the evens are the 2 times something. The set of all the real numbers be strictly between -2 and 7. So I can call the x that belong to R real numbers. And there are between -2 and 7, strictly. So I should not put this equal here. So strictly here. The set of all integers that are multiples of 5. So once again, x belongs to C. So x is a multiple of 5. Phi n. This is another way of writing that. Now, you can also write this as phi k with k that belongs to C. There are many ways to write in this. Make sure to check the solutions for checking alternatives to this. Now, consider the set n that belongs to C with n squared less than 20. Let's write S using set rooster notation. So if we're doing set rooster notation, this first means that n squared is less than 20. So that means that n is going to be, or the absolute value of n is less than the square root of 20, which is around 4.47. But we're using integers, so that's pretty much going to be less or equal than 4. So S is going to be the numbers between -4 and 4. So -4, -3, -2, -1, 0, 1, 2, 3, and 4. This will be my x's. Now, is 4 in S? Yes, it is in there. Is 5 in S? No. How many elements does S has? You can count the elements here. This is 4, 5, and then 4 more, 9 elements. So that way you can kind of figure out how many elements is in there. You can also check if an element belongs because it matches the condition. So 4 squared less than 20 will be 16 is less than 20. Yes, it is. 5 is less than 20. 5 squared is less than 20. No, because 5 squared is 25. So that won't work out. Okay. Question 11. True or false? For any set A, the empty set is a subset of A. Yes, this is true. The empty set is in any set. For any set, A is a subset of itself. This is true. Remember, all the elements from here are also here, so that's going to work out. Now, if A is a subset of B and B is a subset of C, then A is a subset of C. This is true. And this is something that you can kind of see in this way. So let's assume that this is the set B. Sorry, this is the set A. And that set A is in a larger set B. So this is what I mean by A is containing B. But it's also, let's assume that B is a subset of C. So we're going to have this relationship. And by obvious reason, A is going to be a subset of C as well. So this is true. Is the set formed by 1 belong to 1 to 3? No, this is false. 1 belongs to 1 to 3. But the set by itself, the set of just 1, is not in the list of elements. So for belong, you got to show on the list of elements, or you got to match the condition of the set. And this is not the case. So this is false. This is true. Okay. Now, last on our examples for section 1.2, we have the set A equals x squared equals 4. Let's write A using rooster notation. And so because we're looking for the number so that x squared equals 4, this is going to be simply 2 elements. It's going to be minus 2 and 2, which are the elements that square give me 4. Is 2 an A? Yes. Is minus 2 an A? Yes. Is 4 an A? No. Because 4 squared is not 4. 16. All right, so this is just checking that something belongs using the property. Now, we have, for the last question, M is 2, 4, 6, and N is 1, 2. Once again, we're doing the Cartesian product. We have here 2, 1, 2, 2, and then 4, 1, 4, 2, and 6, 1, 6, 2. And this has numerical elements and everything, so you got to be careful. How many elements do we have? We have 6. Once again, 2 times 3, 6. If A, B is in M times N, what you can say about A and B? Well, by the definition of what the Cartesian product is, you can say that A belongs to M, and you can say that B belongs to N. That's it. And you can also say that A can be 2 or 4 or 6, and B has to be either 1 or 2. That's the options that you can have here. All right, that concludes the example for section 1.2.